we start? Okay, so yeah, today we are going to cover transistors and MOSFETs. We are going to start with transistors, and basically the two main focus here we will be touching on is the NPN and the PNP. Now MOSFETs are just they're just a subset within the transistor family, so we'll talk on those later. And we're specifically only going to touch on N-channel MOSFET and P-channel MOSFET. There's a wide range of different FETs that all achieve similar behaviors. Some actually have a little bit of different, but for what we deal with in basically all application can be covered with just discussing the NPN, the PNP, and then for MOSFETs, NFET and PFET. So to start, transistor off the bat, it's a semiconductor device. And it's typically used for switching and for amplification, or amplification, I guess it is the better. And the distinguishing aspect between a transistor to a MOSFET is that these are current regulating devices. Or current controlling devices. This sums up for both NPN, PNP. They both follow the same kind of definition. It's just that their behavior between the two will act differently. So if we start the NPN, it is a three-leg device with base, collector, and emitter. Now we have three primary operating regions. We have cutoff, active, and saturation. So starting off with cutoff, as it's going to be the easiest to describe. Cutoff is when, or let's step back one more even. We can imagine the transistor to behave like a switch, as we said, that gets controlled by our base pin. So current wants to flow from collector to emitter, and only with the activation on the base pin can we achieve such a behavior. So when we are in cutoff, this is basically we're sending no current to the base. So by not sending a signal on our base pin, keeping this just a 0, it's not going to trigger the switch to close. So what we'll have is just an open switch. So we won't have any current flow through the device. So in sense, we have effectively what is switched off. So it blocks current, it lets nothing through. And it's simple. Good so far? Questions on general description or first operation mode? Now we can run into saturation, which is it's when we are now going to actually be sending a signal on the control on our base pin, and this is typically known as the fully on state. So we have, when we send a signal, when we have a voltage on the base that is larger or equivalent to our voltage on the collector, we will see that it closes the gate, and it essentially causes a short between collector to emitter. So this state is essentially switched on. So this is the operation region for a transistor when you want to use it as a switch. It'll either be, you either send 0 for it to be in cutoff, so switch open, or you send it the equivalent voltage that's seen on the collector pin to saturate it and cause a short, basically closing the switch. And finally is the active region. This is the kind of special region to the transistor. This is where it can distinguish from a MOSFET, and this is where the current regulating portion of the device actually comes into play. So again, we have to be sending a signal on the base, and it'll cause the switch to close, current flow. But in this case, instead of sending the same voltage that's seen across the collector, we will send a signal that is just greater than our threshold voltage, which in transistors is typically, much like diodes, it's going to be around 0.7 volts. So by sending a signal that's just beyond our threshold voltage to cause it to close, but not sending it by still sending it a voltage that's lower than the collector, it's now going to be in its active region. And in this region, we can start to control our output currents. So what that means is we can see that our collector current, so the current that will flow through the device, is now going to have a relationship to the current that's seen on the base. Any quick questions on where we're at so far?
What does beta represent?
Yeah, so beta is the saturation constant, I believe is what it's called. Yeah, geez, I can't remember exactly. It's basically the saturation constant. So in most transistors, beta will be usually below 100. I think 20 to 100 is the typical value. But it is it's just a saturation constant. You'll be able to find in the data sheets of any NPN, it'll explicitly have this beta constant, letting you know what it is. Anything else on this so far? Let's have it. So with this, it means we can precisely control what our output current is based on whatever we feed it to the base. And that also means we are able to control this with small, we're able to control this with small currents. So say only 5 milliamps to actually turn this device on. But if we have a beta of 100, we're going to be able to boost it so our output current, or our collector current, is going to be much higher. So we're able to now amplify and control what our output current is going to be based off of our input. And this is generally just done resistor on your pin. If you know you have a 3-volt signal, whatever resistance value you choose will give you your base current. So you're able to tweak your current to change your collector current that flows through. Make sense? Something probably should have started with, now that I look at my notes, what we need to see to be turning on the device, which kind of made note of, is we need a positive voltage between your base and emitter to be able to turn on. And this positive voltage has to be of the value of your threshold voltage, which is, again, 0.7. So if we were to have some 1 volt on your emitter, you would have to be sending something greater than 1 plus your threshold to actually be able to turn on the device. So it's not about just hitting the difference between your pins has to meet the threshold. We will see someone.
Is the threshold voltage always 0.7, or it depends on the transistor thing?
It depends on the transistor. Typically, I believe they're going to be 0.6 to like 1.2. It is going to be a low number, because I believe in essence what we're looking at here is 2 diodes. You're basically looking at a transistor can basically be broken into a couple of diodes, and as we saw in our previous lesson on diodes, their threshold is typically 0.6 to 1.2 volts. So same behavior. We have to reach that to be able to allow a path to flow through.
Oh, okay. Thank you.
Anything else? Then we hit, yeah, so we can typically break up our transistor into 3 general configurations. Being your common base, common emitter, and then common collector. Now, what these are basically how, or what pins are basically shared between input to output. So a common base will look, what we got? What do we have? These, yeah, your common base is going to be basically shared through your device. So input to out. Typically that would mean like you're grounded and you have your V out, which is then also referenced to ground. Same with your input, whatever your V in, it's of course going to be referenced to ground. So you can see this can be typically drawn as such. So you can see the node to base is shared between in to out, where we'd have our signal pin coming into control. Now, when we have it in the common base configuration, we can see we can create a voltage gain, but no current gain. Similarly, if we do common emitter, we can achieve voltage gain as well as a current gain. And then finally, if we're doing common collector, we can get current gain, but no voltage gain. So by using the same, did I get this right? By using the same transistor in just slightly different configurations, we can achieve just by minor slight configuration changes, we can achieve different outcomes. So if we wanted to hold constant current and modify the voltage, if we wanted to achieve both constant voltage and a current gain, we can set it up in a constant emitter. And then same constant collector if we only want to see a current gain, which is quite typical of our setup, or of quite common design that's used. Do these can make sense? Or do just general questions on these? what does a emitter look like? Is there really nothing? Nobody has anything on this? I want some questions, because again, I don't believe that I'm explaining this well enough that anybody can 100% say.
What can we use this for?
So constant, sorry, not constant. Common collectors can typically be used for they can be used for buffer systems. Or
Sorry, what is that?
Buffer is something I will go into more detail in another lesson on op amps, because that's a little more direct. But basically, it's a way of keeping or applying a greater current output when otherwise you wouldn't have enough. So in some microcontrollers, you're only able to source, say, 5 milliamps, and maybe you want to turn on an LED. Now, from what we remember, typical current for a LED, they like to see 20 milliamps. So in this case, where it'll light up dimly or not at all based off of the capabilities. So what we can do is throw a transistor in the loop. So we can, or I guess, so we can now pass it through to boost the current in this case, and actually be able to turn on our LED. So that is your, you'll see that commonly on, so the common collector configuration can be used for boosting your current output while holding steady, because again, say this is a 3v3, which is sufficient to turn on the LED. So we don't want to change. We don't need to change that. We don't need to increase. We don't need to increase the voltage use, but we just want to be able to increase that current. Similarly for common base, it can work in the opposite. Yeah. So what did I just? That's kind of your CC use, and then a common base use being that it increases voltage but not current. So this is particularly useful when we're using it on an AC signal. We may have a low magnitude, small voltage AC signal coming in, and then we are able to create a voltage gain so that our output voltage is a much larger magnitude without having to do much modifying of the signal. And then the common emitter, it can be used for both of these, since it has the ability to increase both current and voltage. So it's possible to use the common emitter configuration if you wanted to do either, since it's capable of doing both of these tasks. Other questions?
What about for the common emitter one?
Yeah, so again, like the common emitter, it has the capability to do both voltage gain and current gain. So you're able to swap it in, do a common emitter to achieve the same thing here, slight configuration change, or do a common emitter on this one, because again, it can do either voltage gain or current gain. So it has the same functionality as both of these. It can do both of these simultaneously. So I guess one thing, if you wanted to keep the same example of our MCU that only has 5 milliamp and 3.3 volt, that probably doesn't have enough to power 2 LEDs. Because like we saw when we went over LEDs, there's a voltage drop across both. So in that case, we can draw up we can throw in a common emitter, so that we can boost both the voltage as well as the current. So there will be a sufficient drive to actually power a slightly larger load than maybe the bit pin is even capable of.
Okay.
Are common
Thank you.
emitters less efficient in any way?
No. They all share relative identical efficiencies, because the structure of the device, it's still just an NPN transistor. It functions, it can do the same, I mean, they're all doing the same thing, just increasing their gains because they are based off of whatever external circuitry you have. So the inputs, the base resistor and collector resistors in one configuration compared to the other, you may be using more. You may be using more resistors, which will have their own losses, and that's what will potentially make a circuit one of these less efficient compared to the other. But functionality-wise, transistor to transistor, it's all basically same efficient.
When do you use an NPN transistor and a PNP transistor?
Yeah, so good. So yeah, like kind of the final point I have on NPNs is their typical use case is as a what do I have? As a low side switch. Whereas PNP will be a high side. So what this means is you'll have your transistor and you'll send the emitter to ground, and whatever load you have will be that you want to be energized will be above it. So it acts as a switch that happens on the underneath your load. So it's known as a low side switch. Whereas a PNP will work the opposite. Now this, it's used as a low side switch, opposed to being a high side switch, because of what we mentioned before, where the voltage difference here has to be greater than your threshold. So if your emitter is always set to 0 volts, it's not too challenging and power intensive to be able to send a threshold that's greater than, to send a signal that's greater than your threshold. Whereas if you're using it as a high side, when you're energized, your emitter may have a greater voltage and it'll instantly turn itself off, or you have to supply a larger threshold. So if we were to see it as a high side, when we switch it on, because of the internal voltage drop that's created in a transistor, we'll have, let's say we have 3v3. We will see some voltage drop across the item, whatever, putting it at 2.5 volts maybe, before it goes through another voltage drop through the load and hits 0 volts. But that means the difference between your base and emitter, you now have to be sending some signal greater than 3 volts to be able to have this actually turn on. Otherwise, whereas if you're using it as a low side, you just have to send it bare minimum to get over the threshold. its use case is typically a low side because of the simplicity of its operating. Any other questions on this? Okay, so that's the NPN. So if we slide on into the PNP, similar design, where it's base emitter collector. Primary, your distinguisher is you have your arrow pointing in from emitter to base, where the NPN was pointing out. So it has the same operating regions, so it will have the same, it has the same cutoff, saturation, active, in a slightly different behavior. I had that. So what we saw before, where we needed, for the NPN, we needed to see a positive voltage cross base to emitter to be able to turn on. For the NPN, we need to see a negative voltage across base to emitter to be able to turn on. So its operating regions are, in sense, inverted. So in this case, if we are sending it if we were sending a signal on the base, and some 3 volts to the base, if we have a, so if we say we're supplying off a 3v3 and we try to send the base a 3v3, that'll see it as no voltage drop. So your switch will remain open. Where if we send 0 volts while we have 3v3 on, now because we see a negative voltage drop from base to emitter, the switch is going to close and will allow current flow. Make sense to the difference on the NPN to the PNP on its operation mode?
Is there any like threshold voltage thingy like in the NPN?
Yeah, so the logic still follows. We will have a threshold of it's generally shown as negative 0.7. Again, this is going to be a minor range of whatever 0.6 to 1.2 or whatever the threshold may be. But yeah, we will still see a threshold voltage on for the PNP as well. But yeah, we just see it in a negative fashion because it's no longer base being larger than emitter. It's backwards, so we have it. Negative voltage drop. And then again, we can set this up in the same way, having a common base, common emitter, common collector setup. So it'll be the same functionalities. You'll see same voltage gain, no current, gain, current gain, no voltage gain. And you'll use these in different scenarios. So I think I actually drew this potentially wrong for one of these. Maybe regardless. Again, they can be used all in the same way to boost current, keep it same, boost voltage, keep current same, or boost both. It's just a matter of if you're placing your transistor system either high side or low side of your load, you would use a PNP or an NPN depending on which way you'd be going. Yeah, so if we're to show that kind of use as a high side switch now. So what we'll see is your transistor will be placed above the load. So your loads, whatever it may be, will always be connected to ground and not 5 volt. I believe there are some stability differences between a PNP and an NPN. I can't say for certain what that is. There is some slight operation differences between a PNP and an NPN to why you would potentially want a higher low side switch strictly based off of transistor properties. But when you're using them, you'll often see it as if you want your system to function with a PNP, it would be placed above your load, whereas an NPN is placed underneath. Questions on any of this? Makes sense how we have to see a negative voltage. Understand why we wouldn't be using the PNP as a low side. Yeah, can somebody tell me why we wouldn't be using it as a low side? somebody. Nobody? I don't believe nobody can, or you're not asking questions and then you're all just confused. Come on, answer. Justin? Alexis? Elena? Anybody? I'll run through the list.
I'm confused.
Okay.
What's the difference between a low side and a high side switch?
So this is high side. This is low side. So your physical switch is placed above your load, making it high, or your switch is placed below the load, making it a low side switch.
Okay, got it. And for PNP we need to use a high side switch, and for NPN we need to use a low side switch. Is that correct?
Yes, that's the typical use case because it's the easiest use case.
Okay.
But why? Why is this inefficient, or why would this not work? PNP is low side switch.
Is it something about the negative voltages we just talked about?
Yes, absolutely. So if we want to swing back up to the NPN, so we were going on the NPN on, it wants to run as a low side. But when we put it as a high side switch, we saw your emitter had a higher voltage, so your base had to have a higher voltage. Now it works basically inversely, because we want our negative voltage across the emitter to base in this case. But we will see that if we start off at 3v3, your load is going to create some voltage drop. And then our transistor, because of its internal threshold and its voltage drop, which is some 0.7 or whatever 1 volt that it is. And then at this node, we're obviously tied to ground. So our load is going to cause some 2 volt drop. So we're now only looking at 1 volt, maybe even less on our at the emitter. Now, if we're supplying our threshold is, if we were to call it -1 volt, applying 0 volts hardly makes the cut here. and if we were to be using an even lower input system voltage, or the voltage drop across is even greater, what we'll see is that maybe this node is only after all the voltage drop would be sitting at 0.5 volts. In that case, we would need to apply minus 0.2 or whatever is remaining to make up the voltage threshold, but we would have to apply a negative voltage, which is much more difficult to do instead of just applying ground, applying a 0 volt. So that's why we'll see it being used as a high side, because it's directly tied to your system voltage. So right off the bat, it's 3 volts or whatever your system voltage is. It hasn't gone through any voltage drop initially. So you don't have to worry about potentially having to apply a negative voltage. Does that make sense to all?
Yeah.
Was that confusing everyone, or does everyone just not want to talk?
I just don't have much to say. It all looks good.
Properly made sense? Like, you understood why voltage are dropping?
Yep.
Why you're using? And everyone else, did it actually make sense? Am I just that good at explaining, or I'm just not feeling like...
It makes sense on my side, but yeah, I don't know, it makes perfect sense to me. But I guess it might help if you show the same math on the high side, unless you already did that.
Yeah, I kind of ran through.
Okay, so yeah, this guy. So yeah, it makes sense.
Okay. That is basically everything I had on transistors. Now, I notice we're already at an hour for this lesson, and MOSFETs would probably take an additional hour, or close to. So if you guys are fine, we can run on and make this a long lesson, or we can stop it at this point and do next session completely on MOSFETs and see how far we get on it. Opinions? Do you guys have time?
Do it next week.
Is there a meeting today?
Yeah, we'll have a general meeting here as well.
Oh, okay. That might go up till 9 then.
Yeah.
So, yeah, next week is fine.
Okay.
Yeah, I think next week would be better.
Okay. I will. Actually, I do have one other little thing on transistors. Yeah, so I'll just do up this final kind of transistor application, and then we can call it. Ask questions, discuss whatever, and then if that's it, then we'll just move into a general meeting after. So kind of the last thing I'm gonna touch on is the Darlington pair. Now, typically this isn't generally something you would design out externally on your own. But this is a use case of the transistor that is very commonly used within components, because it is structured as 2 NPNs. And I'm sure it can be made with 2 PNPs as well. But basically tying your transistors to each other, so they share a collector, but then you control one, and then the emitter feeds into base, and then you have your final output on the secondary. With this transistor configuration, what we're able to accomplish is beta multiplication, which is the which again is the current kind of current multiplier constant. So when we set it up in this pair, what we're able to see is our current multiplier from both. So like your beta 1, whatever that'll be in your beta 2, will actually be multiplied. So by setting up this configuration, we can achieve a much greater output current. So if we were to say, again, both just had a constant of 100, if we had it in just an individual with a beta 100, again, because of your multiplier, we can see an output or a collector current drastically increase. Now by doing this configuration, again, if we still can only apply 5 milliamps to our base, we get the amplification through 1, and now again we're going to multiply by an additional 100, so we can achieve your output current is now grown to a much larger value. So we can now switch, a greater than 1 amp load by only triggering off of a 5 milliamp signal. Doing this, your voltage drop obviously again is also going to be doubled. So voltage drop across just one was only going to be 1 volts or something of that, because we are adding 2. The voltage drop in this case is going to be 2 volts. You obviously have to double it when you're because of the configuration. But it's a highly used configuration within components, and can also be used externally if you are in a case where you're toggling at such a low current draw, but have high load applications. So this can commonly be seen in, these will be seen within power supplies, within LDOs, because the internals of linear regulators are often, they often have a low input internal voltage, 1.3 volts, and it's a low current draw system. And because you're switching it across a proper 12 volt down to 5 volt, or 5 down to 3, some proper power application system, it's going to require a large current draw. So in that case, the internals will often look like this, so that they're able to achieve such a large current draw without having to drastically increase component size or specs. Questions on the Darlington pair? It is a little more advanced than what you'll generally design. Again, this is typically used already within components. It'll be inside of LDOs and main chips. But yeah, it's not a hard concept to understand how we get such a large amplification, but it's a useful one.
Is Darlington pair used in any of our boards, like the power distribution or anything?
No. The power distribution uses buck converter.
Just the buck. Okay.
Which
Current doesn't.
It may internally, because yeah, I think some buck converters are, they will use transistors instead of MOSFETs to do their switching, because the operation is just switching. So in transistor-based bucks, I'm sure they would use the internals would have Darlington pair to allow for the high current drop. But it's more typical in LDOs and linear regulators compared to bucks.
Jarod?
Yep.
I see you wrote beta multiplication. Is that right? Okay, thank you.
Yes, I'm good at English.
Simplification better, but like.
Yeah, anything else on this? Okay. Then, if there is nothing else, that concludes transistors. And yeah, since we're already over an hour, we'll set MOSFETs for next week. So